Hi there. We're going to talk about cross product today. The cross product is a second multiplication concept for vectors that we're introducing. So we're going to define it now. The cross product is going to be denoted of let's give the vectors. The vector A is going to just generally A1, A2, A3, it's three components, and B with B1, B2, B3 is given by this formula. Now we use the times symbol like you did when you probably first learned multiplication as a kid. It's a vector, and I'm going to give it out in its full form. Now it's A2b3 minus A3b2. That's the first component. Then we have A3b1 minus A1b3, and then we have A1b2 minus A2b1. Now this is a hard one to memorize, and I certainly don't expect you to memorize it. It's equivalent to being written as a determinant. Now, determinant is it's a linear algebra thing. It's a way of taking, if you have a 3x3 matrix, which is just a grid of numbers. In fact, I'm going to cheat a little bit. In the first row, I'm going to put the three basis vectors, the standard basis vectors. Oops, let's do A1, A2, A3 in the second row, and the last row B1, B2, B3. So a determinant of a 3x3 matrix is just a way, it's a mathematical operation of the matrix. It's going to be the I vector times the submatrix that you get when you take away the first row and the first column, A2, A3, B2, B3, minus the J vector times the submatrix you get when you erase the first row and the second column. So that's going to be A1, A3, B1, B3, then plus. So notice the sign change. This is plus, minus, and then plus for the third one. And then we've got the submatrix you get when you take away the first row and the third column. So it's the A1, A2, B1, B2. And each of these, this is the I times, what you get is you take the diagonals, and you take this diagonal product minus that diagonal product. So it's A2, B3 minus A3, B2 minus the J vector times A1, B3 minus A3, B1, then plus the K vector times A1, B2 minus A2, B1. This is what we have up above. Instead of putting I, J, and K, we just put those in the first, the second, and the third components. So this is the formula, and doing the other way that you can do a determinant is if you have I, J, K. Well, this is a method that I kind of like. A1, A2, A3, B1, B2, B3. Let's just tidy up that a little bit. What we're going to do is I'm actually going to put in, I'm going to repeat the first two columns, the I column and the J column, kind of over to the side. A1, A2, B1, B2. What I'm going to do is have three products that are going to be positive. So this product, that product, and that product are going to be positive. So we're going to have, we have I times A2 B3 plus J times A3 B1 plus K times A1 B2. Now we're going to have three products that are negative. This one, and this one. So we'll have minus minus the first one in the order is K times A2 B1 minus the next one is the I times A3 B2 minus J times A1 B3. I find this pattern to be a little easier to do in practice, but it really depends on your style. We'll do examples in both. Let's do an example right now. We'll do A is the vector 1, 3, 4, and B is the vector 2, 7, 5. Sorry, negative 5. Let's do. Okay, so A cross B. I'll write this matrix for the determinant I, J, K, and we have 1, 3, 4, and 2, 7, minus 5. Let's do the first method. It's the I vector times 3, the determinant of 3, 4, 7, minus 5, minus the J vector times the determinant of 1, 4, 2, minus 5. So what I'm doing is I'm leaving off the second column, plus the K vector times the determinant of a 1, 3, 2, 7 matrix. So this is going to be I times 3 times minus 5 is minus 15, minus 4 times 7 is 28. So the first diagonal product, so this is plus, and then this one is minus. So, but then we have minus J times 1 times minus 5 is minus 5, minus 4 times 2 is 8. Now we have plus K, so 1 times 7 is 7, minus 3 times 2 is 6. This is, I'm going to put the i's second, so minus 15 minus 28, this gives us what, 33, 43 minus 43i, and then we have minus 5 minus 8, that's minus 13, times minus is plus 13j. Now we have 7 minus 6 is 1, so it's going to be plus k. So what we observe right away is when you do a cross product, you get a vector. It takes a vector times a vector, and you get a vector. I'm going to show you another cross product example. Let's take some vector A cross itself and just see what you get. So we have I, J, and K. We've got A1, A2, A3, B1, oops, A1, A2, A3. So I'm going to, let's do the same thing I did before. We'll see, actually let's do the second method, just I'll repeat the I and the J, and then A1, A2, and then A1, A2. Okay, so what we're going to have is these diagonals, so are all going to be positive. So we have I'm going to put the A2, A3, I'm going to put the I second, plus A1, A3, J, plus A1, A2, K. Then we're going to be subtracting the other diagonals. the other diagonal products. Okay. This is a little bit, I'm getting over the edges a little, so these are going to be all minus. Minus A1, A2K minus A2, A3K minus A1, A3J. Notice what we got here, though. We have A2, A3I plus, did I make a little mistake? I did make a little mistake. The second one should be I, not K. That's an I. Okay, so back what I was about to say. A2, A3I minus A2, A3I. So this and this cancel. And then we have A1, A3J minus A1, A3J. That cancels. A1, A2K minus A1, A2K cancels. So what we get is just the zero vector. So here's a fact. Any vector crossed with itself will give you the zero vector. So let's state a theorem. A cross B is orthogonal to both A and B. Is a fact. The cross product is orthogonal to both vectors A and B. So we can prove this actually in general. And the proof is pretty straightforward, in fact. What we're going to do is just evaluate what is A cross B, dot A. Because remember, if two vectors are orthogonal, that's the same as saying that their dot product is 0. If this dot product is 0, then they're orthogonal. Okay, I'm going to use the since I already have the formula for it, I'm going to actually write it out here like this: A2 B3 minus A3 B2, comma, A3 B1 minus A1 B3, comma, and then we have A1 B2 minus A2 B1, and the dot product of that with A1, A2, A3. And just see what we get when we multiply this. So what we're going to get is we have A2, B3, A1 minus A3, B2, A1. So that's just the first component of the first vector times the first component of the second vector, plus A3, B1, A2 minus A1, B3, A2. That's the second component of the first vector times the second component of the second vector, plus A1, B2, A3 minus A2, B1, A3. And if we simplify this, we'll notice that we get some canceling. So what do we have? Let's see, A2, B3, A1. Let's see if there's another A2, B3, A1. That's here and here, right? Those are going to cancel. I'm going to do in green the next canceling. We have A3, B2, A1, and then we have A2, let's see, A3, B2, A1 over here. Those are going to cancel. And then let's do the next one in a blue. We have A3, B2, A3, B1, A2, A3, B1, A2, all there. So we get not the zero vector, but just the number 0. So they are orthogonal. Yep, that's not too bad. And you can A cross B dot B is the same ish, pretty much the same. All right, so the cross product takes two vectors, and it will give you, so if you have two vectors in space, this is vector A, this is vector B. The cross product is going to give you some new vector, A cross B, and it's going to give you a vector that's orthogonal to both. I'm going to make those right angle things a little more obvious. So this, actually, let's make that a little bit more up. Okay, so this is to illustrate that this new vector is orthogonal to both. It's in 3D space. Cross products are only defined for 3D vectors. There's no cross products of 2D vectors or 4D or anything like that. The direction of A cross B is given by the right-hand rule. The right-hand rule says that if you take your fingers if you take your right hand with your fingers curled around in the direction from A to B, then your thumb is going to be pointing in the direction of A cross B. So using your right hand with his like curled fingers, that gives you the direction of A cross B, which tells you that B cross A will be pointing in the opposite direction. Let's see. Another theorem is that this is similar to a theorem that we have for dot products. If theta is the angle between A and B, then such that as long as it's an angle that's between 0 and pi. So we're taking the smaller of the two angles, the angle that's less than 180 degrees. Then what we have is the magnitude of the cross product is equal to magnitude of A times magnitude of B times the sine of the angle between them. And so the proof of this is going to kind of happen in a couple parts. The first thing we need to kind of verify is we need to verify that A cross B squared, the magnitude of A cross B squared is equal to magnitude A squared times magnitude of B squared minus A dot B squared. This is actually a bit tedious, so I'm going to just say trust me that this, I'll put those vector signs above A and B. So the magnitude of A cross B squared is equal to the magnitude of A squared times the magnitude of B squared minus A dot B squared. A dot B is going to be a scalar. So you have a scalar minus a scalar. And we can now use a substitution that on the right hand side, because what do we have? What is the dot product? Is simply the magnitude of A times magnitude of B times the cosine of the angle between them. So this is a theorem from the previous section. The dot product is equal to the magnitude of A times magnitude of B times the cosine of the angle between them. And now we can expand out this side. We have magnitude of A squared, magnitude of B squared, minus magnitude of A squared, magnitude of B squared, cosine squared theta. Notice we have magnitude of A squared, magnitude of B squared as a common factor. 1 minus cosine squared theta is what you get when you factor that out. And if you remember your trig, 1 minus cosine squared theta is the sine squared of theta. And the sine the sine of theta is greater than 0 because theta is between 0 and pi. And so we can now just take a square root of both sides and we can state our theorem result is right there. That wouldn't necessarily be true if the sine was negative, but for all these angles the sine is always going to be positive. So that's the result. We can square root both sides and then we can get our answer. So that's a result about the cross product. So what we're saying is the cross product is going to so the cross product gives you a vector, right? The magnitude of this vector is going to be affected by the magnitude of the two vectors and the angle between them. for cross products, remember sine theta is max at theta equals, I'll just say it in degrees, 90 degrees. So when the two vectors A and B happen to already be orthogonal, then their cross product is going to have a maximum magnitude. And as the two vectors either are more in line with each other or more apart from each other, the cross product is going to get smaller and smaller and smaller in magnitude. Okay. Here's a corollary from that. So A and B non-zero vectors are parallel if and only if A cross B is the zero vector. And this is actually also what this would mean in the determinant. The two vectors A and B, basically one is a scalar multiple of the other. I'll say also A and B, this is not the corollary, but this is just a fact about vectors, are parallel implies that A is just equal to some constant times B for C for some real number. This is another way of knowing that two vectors are parallel. So if B is just a scalar multiple of A, then you know they're parallel. If they're parallel, then the cross product will be zero. Something that's interesting about the cross product is that the magnitude of the cross product is going to be, if you have two vectors B and A, what I'm going to do is I'm going to copy these and create a parallelogram. So this vector up here is also A, and this is also B. The area of a parallelogram with sides A and B is equal to, I'll say equals the magnitude of the cross product A cross B. And that's actually, you can see that if you were to work out the formula for a parallelogram's area. It's just base times height. The height, if this is the angle between these two vectors, this is going to be the sine. It's going to be magnitude B times the sine of theta, right? So so base times, I shouldn't use the cross, I'll just use base times height is just the base, the length of the base, and then the height is just the magnitude of B times sine theta, and that's magnitude of A cross B. This is just a fun fact. I'll put it in fun fact. A fun application of cross products. Okay, so let's see. So what you can use this to find the area of triangle given 3 points. Let's find the area of a triangle with vertices A at coordinate. I'm going to use P, Q, and R. P 1, 4, 6. Q negative 2, 5, minus 1, and R 1, minus 1, 1. So this is going to look something like this. This is in 3D space, so I'm not being so precise, but basically get P, Q, and R. Now, if we if we think of this in terms of vectors, this is the vector PQ, and that's the vector PR, and here's the area, the angle between them. What I was just saying is, like, if we were to make a parallelogram, the area of the triangle is half the area of the parallelogram, so it should be 1/2 times the magnitude of PQ cross PR. That should be the area of the triangle, because the area of the parallelogram is just the magnitude of PQ cross PR. And what is PQ? We have to take the difference. PQ is the vector. We take the components, the coordinates of Q, and subtract the coordinates of P. So it's -2, -1, 5, -4, and -1, -6. So this is going to be -3, 1, -7. PR is, take the coordinates of R minus the coordinates of P, so it's going to be 1, -1, comma, -1, -4, comma, 1, -6. Which is 1 minus 1 is 0, -5, and -5. So now we want to find what is PQ cross PR. PQ cross PR is going to be IJK, and then we have in the second row we've got -3, 1, -7. We have 0, -5, -5. Okay, we've got I times the magnitude of -3, 1, 0. Oops, that's a mistake. It's 1, -7, -5, -5, minus the j vector times -3, -7, 0, -5, and then we have plus the k vector times -3, 1, 0, -5. All right. So this is going to be what? The first component is 1 times -5. That's -5 minus 35. Then we have minus minus 3 times -5 is 15. Minus 0. Then plus -3 times -5 is 15 minus 0. Okay. This is -40 minus 15 comma 15. And so our answer, 1/2 times the magnitude PQ cross PR. That's 1/2 times the square root of 40 squared plus 15 squared plus 15 squared. And okay, now some properties of cross products. The first property is that the cross product A cross B is, I mentioned this earlier in passing, the negative of B cross A. So if you switch the order, you don't have the same cross product, it's going to be the opposite. It's going to be a vector going in the opposite direction. Now the commutative property, or I'm sorry, the distributive, this is the associative property of scalar multiplication. Some scalar times a vector A cross B is the same as the scalar times A cross B, which is also the same as A cross CB. So you could have that scalar in either of these places. You can in fact factor a scalar out of the whole situation. The next is a form of distributive rule. A cross B plus C is A cross B plus A cross C. Now the distributive rule kind of works backwards as well. So if you have A cross B I'm sorry, I wanted to have A plus B, the sum of two vectors, cross a third, will be A cross C plus B cross C. Right? Fifth thing is known as the scalar triple product. The scalar triple product says that A dot B cross C is equivalent to A cross B dot C, which could also be written as the determinant of the matrix A1, B1, I'm sorry, A2, I did it again, A3, B1, B2, B3, C1, C2, C3. And the last property I want to mention here is the cross product of three vectors. Because you know cross product gives you a vector, so you can cross a cross product with a product, cross product, cross a vector with a cross product. This is A dot C cross B minus A dot B cross, times C. This is a funny one. A very kind of a funny one. Wait, I think I didn't want to have a. This is all just times. Put that over a little bit. Okay. Yeah, it's A dot C scalar product with B minus A dot B scalar product with C. So those are the properties of cross products I wanted to mention. I want to move on now to an example, an application of cross product. So so torque is rotational force. So torque, here's the formula for torque. It's the positional vector of where the torque is applied cross the force vector of the direction in which the force is applied. So R is the positional vector where the force is applied, and then F is the force vector. So let's give a little example. I'll try to illustrate it. So here's my z-axis, my x-axis, and my y. So let's suppose that we have a bolt and a wrench. Okay, so the bolt we want to apply torque to tighten the bolt. So this point here, the vector going from the origin to the point where let's say we're gonna push down in like that direction. That's my force vector, and this here, that's my R vector, is like the point where I'm applying the force. So then my torque vector is going to be going in that direction. The torque is going to be the magnitude of the torque is the amount of force applied in that direction, and the direction of the torque is like where that torque force is going. Hopefully I'm using the terminology of force correctly, but so for example, if a let's say a 20 centimeter wrench is on a bolt going in the negative x direction, as I've pictured here, and let's say a force let's see, it's 0, 3, minus 4. This is the force vector that I'm applying, is applied, and that's in newtons meters. Oh, actually, that's the force units are in meters, so I want to convert this. This is going to be, that's 0.2 meters. I'll be dealing with meters. So this is the amount of force that's applied. Let's calculate the torque. The torque is going to be the position of this is actually 0, 0.2, 0. That's the position vector. That's 0.2 meters in the y direction, but we're going to cross that with this 0, 0, 3 minus 4 force vector. That'll give us the torque. And so this is going to be I, J, K, 0.2, 0, and 0, 3 minus 4. This isn't going to be too bad of a multiplication. It's I times 0.203 minus 4 minus J times 0, 0, 0 minus 4 plus K times 0.203. The nice thing about this is that the determinant of a matrix with either a 0 row or a 0 column is just 0. So these are both going to be 0. And so all we have is I times 0.2 times minus 4. It's 0.2 times minus 4 minus 3 times 0, which is just 0. So this comes out to be minus 0.8 I, which is a vector that's minus 0.8, 0, 0. So indeed, the torque it's applying a torque force in the direction of the bolt, like tightening the bolt. I know I'm like trying to do the right hand rule in my mind, but I mean this is like the righty-tighty righty-tighty rule, right? This is the amount of torque, and so if you want to, I'm sorry, not the amount of torque, but this is the torque vector. The amount of torque is going to simply be the magnitude of this vector, which comes out to be 0.8 newtons meters. So this is an application torque. Now you can use this to find how much force is needed to result in a certain amount of torque. We'll do some examples like that later on. All right, that's it for cross products.